So yeah, I'd like to thank the OpenSSL Foundation for giving me this opportunity. And I'd like to express my admiration of all of you for actually being here at 9 AM, given what's been going on for the last couple of days. So basically today I'm going to be talking about what we've really been doing in terms of like trying to absorb the post-quantum algorithms into the Bouncy Castle APIs. I mean, as you're aware, there's been a couple of talks already mentioned it. I mean, they've basically standardized a set of algorithms, and of course now what's happening is we're seeing different standards that actually utilize those algorithms. Because it's great having a signature algorithm, for example, but you want to be able to create certificates, you need object identifiers associated, you want to be able to use it in CMS, there's a whole range of things. So the timeline for post-quantum from the Bouncy Castle worldview is that we added the algorithms officially in 1.79, which is October 2024, just a couple of months after release. We had actually implemented them a few years earlier as NIST round 3 candidates, but of course, given the nature of things with NIST and the public comments period and various people refining what they'd done once they decided which the finalists were, the actual final implementations didn't appear until October 2024. So C# was slightly further behind, but we actually had them released in C# by December 2024. Private key encoding, is anyone else here on the LAMPS mailing list? Yeah. So there was a very spirited and robust discussion about private key encoding and things like that earlier this year, which eventually got settled. So we've actually started using the official, what's going to be the official format. The only thing I'll say about the private key encoding discussion was there was actually quite a remarkable thing happened because a few of us found ourselves on the wrong end of the bridge, so to speak, because we wound up in the position of pointing out that the proposal to use seed only wasn't actually allowed by the standard. And the amazing thing that happened was NIST actually decided to allow it, which was fantastic. So the actual outcome, despite all the bloodshed, was actually quite a positive one. And so now we support the full thing where you can encode as seed only or as expanded key if that's what you've got, or if you've got both available to you and you want people to be able to cross-reference them, you can use both. We've got Falcon, of course, and we've got HQC. We're doing our best to kind of keep track of what's evolving with those two standards as they're in progress. But yeah, the way it's probably going to go is we'll probably won't be seeing anything in there until 2026. So yeah, what are the pain points? Like, what is the fuss? I mean, there's the obvious one, which is key sizes, signature sizes, key transport packets. They're all a lot bigger than they used to be. I still don't know how they're going to successfully do some of this stuff over UDP, but that's okay. Some very clever person will sort that out. There are 3 ways to store an MLChem, MLDSA key, as I said, because of what happened with LAMPS. But again, it's just ASM1. The reality is you only have to check a couple of bytes. You don't need to write an ASM1 parser to decode one of these things. It's important. I think this is one of the things that people tend to lose a bit. It's important to understand that when people are talking about ASM1 in the context of key encodings, it's a tag length value byte stream. Yes, ASM1, the language, is horrendously complex. The IETF is very lucky because they have their own poet laureate in the form of Russ Housley. But yeah, for the rest of us, it's like writing JCL. You find something that worked and you cut and paste it into your document and you hope for the best. But for this sort of stuff, it's really quite simple. There's no need to be intimidated by it. Now, there's no chems that are suitable for multi-party agreement. So the old game you could play with Diffie-Hellman where you have multiple keys involved and you can all come together to produce one secret. That doesn't currently happen. MLDSA and SLHDSA do consume more CPU. MLChem itself, though, is shown to be pretty efficient. Bandwidth is another consideration. This is particularly interesting because there's a paper on the use of classic McAleese where the researchers discovered that once you absorbed the cost of actually sending the McAleese public key, the fact that the ciphertext was so much smaller, it didn't actually take that many transactions before it was actually faster, which is weird. Well, actually not really weird, but that's the thing. I mean, McAleese public keys can be 1.3 meg, for example. But the ciphertext is so small that if you painted it yellow, you could convince one of your children that it was a Pikachu. You know, it's really, really tiny and cute. Just like the good old days when we were using RSA 512. So yeah, SLHDSA needs to scan the message twice. This can create all sorts of issues, especially if you're dealing with large data. Pre-hash signature forms exist for both MLDSA and SLHDSA. Pre-hash isn't such a big thing with MLDSA anymore because of external mu, which is a way of actually calculating what's essentially a pre-hash, but doing it in the manner that they want. The other thing behind pre-hash, of course, is that it's for situations where you don't actually have access to the public key, because the mu calculation actually involves using the public key. And this is one of the interesting things about some of the discussions you can have with people, because they can't understand why there'd be a situation where you wouldn't have the public key. But speaking as someone who's been working kind of on the edge of the embedded space for quite a while now, I can assure you there are situations where you will not have the public key. And yeah, there's quite a lot of interest in hybrid modes. So using a classical algorithm and a PQC algorithm side by side, examples of that are like composite, which is now in last call, and of course, you know, the hybrid key encapsulation mechanisms, which you can even start using now with a NIST compliant module, because the position from a compliance point of view is that as long as one side of your hybrid algorithm is actually certified, it's good to go. Now, ML private key, I've already talked about the politics, so we've all moved on. So yeah, 3 formats, seed only, expanded only, both the above. The way we support that in Bouncy Castle is we actually have a method on a private key where you can basically pass true. And what that will do is that will actually give you a key that will encode as seed only. The default in Bouncy Castle is both. Now, the true is kind of an aspiration. So if the key is not able to encode as a private key with seed only because it's already expanded only, then you'll get back an expanded key. But if you've generated the key yourself, then with Bouncy Castle, then you know for a fact that you can actually get the seed only format. And yeah, if you're archiving keys, particularly for something like CMP or that, where you don't really want to archive a fully expanded key if you don't need to, using seed only, and you just pass through, and then you can use the private key like you would any other way. In fact, if you wanted to, like imagine you had your own method for returning a key pair, obviously you could just wrap this new private key in a key pair and return that instead. Chem-based key transport, so I've used the secret key at the top, of course. Kids, don't try this at home. That is not how you do it with a secret key, but for the sake of discussion, let's just go with that. In this case, so I'll get to it in a minute because Oracle have added a Chem API to Java 21, but of course we've still got quite a lot of people who are actually using Java 8. And obviously the fact they've added a Chem API doesn't help with C# either. So, in order to support people that are on pre-Java 21 JVMs, we've basically got 2 methods of using chems, both of which really derive from the original RSA chem. I think it was RFC 554 or something. But yeah, NIST also had a standard for an RSA chem, which we'd implemented in FIPS already. In this case, basically, you've got a KTS parameter spec, key transport parameter spec. You specify what wrapping key you use, and what this basically does is it generates the usual chem encapsulation, and then it generates a wrapped version of the key at the end of that, which has been encrypted using the secret key that was generated by the chem. So that's, and if you look at the way the RSA standard originally worked, that's basically verbatim, exactly what it did. Actual key generation itself, though, you can also do, and we've basically leveraged the key generator class in Java for that. Now, one thing that I should have probably mentioned here, by default, there is actually a KDF involved in this as well. So really, if you're actually going to use the secret from a chem directly, you want to be actually using a KDF too. But essentially, we have a generate spec, which, I mean, the names are kind of self-explanatory. You pass in the generate spec if you're actually generating from a public key. And then if you're on the other side of it, where you've actually got the private key, you just use the extract spec. And that will give you back what we call a secret key with encapsulation. Basically, in the second case, it probably could just be secret key because you've already got the encapsulation, but my OCD just couldn't handle that. So we ended up returning secret key with encapsulation for both. And then there's Java 21. So this isn't really a parallel to what the first example I showed with what was essentially the RSA chem construct using Cypher, but this is essentially the same thing as what you can do with a key generator, except it's slightly nicer. Java 25, of course, only came out a week or two ago, and that's now actually got proper support, I believe, because I haven't actually tried implementing it yet, but it's got proper support for KDFs in it as well. But in our case, basically, you just pass an OID, an algorithm identifier, to say what KDF you want to use. Okay, so external mu. This was another one of those things where it was kind of like this throwaway line in the standard, and the IETF, God bless them, just ran with it. And then NIST, God bless them as well, decided, well, yeah, okay, sure, why not? So we support external mu as well. Basically, as you see though, the mu value is not just a simple digest. There's a public key, there might be context, because the MLDSA signatures and SLHDSA signatures allow for context as well. And then basically you get back what's essentially a hash, but a very carefully constructed one, which you can then pass to your HSM or send to someone else and produce a signature or verify a signature, depending on what you're trying to do. So the code for doing that's really quite simple. In the private key case, you basically just say, I'm calculating mu. It gets a little bit weird in this case. So we have a construct called an MLDSA proxy private key. And the reason for that is that in the mu calculation, as I said before, and on the previous slide, you can see that you actually need to use the public key as part of doing it. But of course, in the Java APIs, you can't pass a public key to init sign, because that would be stupid. And actually, look, to be fair, it probably would be stupid. So we actually have a proxy private key that pretends to be a private key, which allows us to inject the public key into the sign mechanism, which then allows us to actually do the mu calculation. Then, of course, you've got deterministic versus non-deterministic. We had a few discussions about this. I mean, strictly speaking, the non-deterministic method is really listed as the preferred approach. But the thing with the Java API, because of the way it works, is the default approach is the secure random would be null. And if you did it any other way, you'd wind up passing null here, which I'm not even sure if it's possible. So really, if you're doing this, you want to think about more what's on the right-hand side rather than what's on the left. But anyway, yeah, as you can see, basically you just pass in your mu value and then you generate a signature like you would normally. Right, CMS. So yeah, no real changes with signatures. It's just that stuff got bigger. Key trans recipient info, which is what we usually use if we're trying to generate envelope data with RSA, has actually been replaced with this thing called chem recipient info. And chem recipient info is a different beast to what was originally specified for the RSA standard under CMS with the RSA chem. It's a bit more thorough because basically we've learned about using these algorithms, I guess you'd say. So chem recipient info carries KDF information and everything. It's a one-stop shop, basically. Everything you need is in there. So here's an example of using a chem in envelope data. I'm assuming everyone can understand what the first 3 lines are about. Generating key pairs and then generating a certificate so we can actually tag the message properly. But yeah, as you can see, the chem recipient info generator, I mean, you just basically pass the certificate and then you say what particular algorithm you want to use as a wrapping algorithm internally, and you say what KDF you want. It's really, really not complicated. Other than that, it just looks like you're using RSA. It's just a different construct because, as I said, with the KDF introduced and all that sort of stuff, the key generation mechanism used in the case of a chem is quite different to what you see with an RSA cipher. And then, yeah, at the bottom, of course, the content encryption is exactly what you'd expect. Oh. I think... Yep, thank you. Sorry, jitters. So, decryption. Again, it's pretty much the same as it is for RSA. You use the certificate to create a recipient ID, which allows you to fetch the particular recipient that was involved, and then you just give it the private key, and you're done. It all works, which is a huge relief. Now, on the PKI front, the thing, of course, is that chems can't actually be used to generate signatures. There is a magnificently complicated paper about using some chem algorithms for generating zero-knowledge proofs, which if that kind of stuff really, if lattice math and everything really rocks your boat, I would thoroughly recommend it. If you get hopelessly confused by that sort of thing, like I do, it doesn't really help. But the point is that there isn't really any way of doing the equivalent to what we can in PKCS10. So at the moment, the proposal really is for, in the case of PKCS10, if you really have to use that, you need to use a MLDSA signature that's associated with the actual key that you're trying to use. And if you're using CRMF or CMP, you can use what's referred to as cert anchor. So the cert anchor is really quite straightforward. The idea is proof of possession basically means that you need to determine that the person that has sent you the public key owns the private key for that public key. So you just send them back an encrypted certificate using their public key. And if they can then use the certificate, that proves that they have the private key, unless there's something very badly wrong with the algorithm. And if they can't use the certificate, then it's not really your problem. I mean, the only big issue there is that if you're a CA, what it does mean is that you, usually with CMP, for example, you'll get a hash back or something so that the recipient has actually proved that they've decrypted the certificate. Because in general, you don't want to publish a certificate saying this is that person's certificate without actually proving that they in fact do have the private key. There's been various disputes about how bad that can be, but yeah, the way things tend to work in security is if you just open the door a little bit, somebody will let in an elephant. It's just the way of the world. So there's 4 proposals for certificate extensions and signature types, which are basically directed towards migration. Chimera, which was originally called Catalyst, but isn't for reasons I won't go into. Chameleon, which is a mechanism for actually carrying a second certificate. So Chimera allows you to dual key. Composite has actually turned into a side-by-side signature algorithm. So in the case of composite, you're basically supposed to verify both signatures now. It's not a one or the other, like Chimera or Chameleon, for example. And then there's an NSA-based standard called related certificates, which is really a mechanism for actually taking an existing classical certificate and saying that this new shiny post-quantum certificate actually is that person over there, which is, you know, I guess it's a distraction process as much as anything, but I guess the NSA are quite good at that. So, Chem certification requests using PKCS10. As I said before, basically what we're doing is we're just using an MLDSA key to convince the other party that it's really us. And then we provide the ML Chem key as part of that and then bundle it up into a PKCS10 request, which then gets processed as you would normally. You verify the signature and all that. And you may or may not send back an encrypted certificate. In the case of CRMF, which is a lot more thorough, this is actually what the cert anchor request looks like if you build it correctly. So to be fair to CRMF, a lot of this is actually CMP, which is Certificate Management Protocol, not Container Manager Persistence. Again, I probably wouldn't use big integer 1 for a message ID, but that's neither here nor there. But as you can see in the CMP message building, you've got a set proof of subsequent message to subsequent message anchor cert, which is basically how you tell your CMP server that I don't want you to try verifying anything associated with the certificate, I just want you to encrypt it and send it back to me. And then at the bottom here, you can actually see where it goes MAC calculator, send a MAC calculator. We're actually validating the password and everything that's associated with the request. Oh, sorry. And then what you basically do is you send back a hash of the certificate to actually tell the other person that you, in fact, were able to decrypt it. So with the hybrid certificate formats, Chimera, the really weird thing about this one, apart from the fact that it's never ever going to, it's one of the only RFCs that's ever been tombstoned, so it's never ever going to be used by the IETF. It is actually fully standardized and has been since 2019. There were some patent issues about it, which is the reason why the uptake was quite poor, and those patent issues probably could have been handled better by the patent holders. But essentially what it gives you is 3 extra extensions. One is for an alternate public key, so that's where your second key comes from, and then you can also specify an alternate signature algorithm and an alternate signature value. The idea really is though that you're using signing keys. This isn't necessarily, this standard wasn't really designed so you could jam an encryption key into a signing certificate. Having said that, I have seen it done already. Anyway, yeah, the extensions are marked as non-critical. So in theory, if you build one of these certs, you should be able to distribute it to a platform which isn't PQC enabled because it will just go, it's not a critical extension, I don't have to understand it. And then you can come back later and sort of update your platform to actually deal with the PQC side. The one kind of catch to it is that essentially there's a different way of evaluating the TBS certificate structure to verify the alt signature value, because obviously the alt signature value is in fact in the TBS structure, and it's very hard to put a value into something which, unless you've got a crystal ball and you can see in the future what it will be, it just doesn't work. But yeah, what it does mean is there is actually, in as much as the extensions mean that there's no changes required to actually deal with these things, it stops very quickly, because if you're doing cert path analysis with these, you really have to update your cert path processing as well. It's not just a matter of adding PQC to the platform. So this is how you create a Chimera certificate in Bouncy Castle. Probably the most relevant thing is down close to the bottom, where we basically say when we've got certgen.build, you can see there's a signer, and you can see, so false in this case just means I want the extension to be false. And then you can see there's an MLDSA signer. So the task of building one, you actually have to provide 2 signers. And then under the covers, the Bouncy Castle class will actually do the TBS alt structure for you and do all the gymnastics behind that before finally producing an actual certificate which has got the extensions populated. And then we have an alternate signature valid method on our certificate holder class as well. So if you want to validate the alternative signature rather than the certificate's primary signature, it's possible to do that. There currently isn't any sort of alternate way of doing this in the Sun JCA though at the moment. There's no real support for this. All right, so Chameleon's in draft. Will it make it out of draft? I'm not sure. Full disclosure, I am actually one of the authors of this. We were all drinking in Yokohama and thought, hey, here's another way of doing it. I mean, the principal advantage of Chameleon is similar to Chimera. You just pass in an extension which is not critical, so you can hide it. But the difference here is that in the case of Chameleon, the extension actually provides a full definition, or rather a template definition of another certificate. So you can use the existing parent certificate plus the Chameleon extension to then build a new, brand new certificate, which is actually a PQC1 or whatever the alternate algorithm was. And the handy thing about that is it means you can leave your cert path stuff alone. It's really just at that point, it's just a matter of actually implementing PQC on the platform that's involved. So here's an example of Chameleon certificate generation. Again, a little bit weird because we have this class which allows you to create the certificate extension called the Delta Certificate tool. There are actually additional options on the builder class to determine what extra items you want to add in the actual template that's used to create the Chameleon certificate, but I've left those out for space considerations. But then, yeah, at the bottom, basically, you can then just extract the descriptor from the extensions, and then you can actually just use the tool again to extract an actual certificate. So X Delta Cert, basically you could actually plug that straight into the JCA if you needed to, and you could actually use it directly without any changes required at all, because at that point the X Delta Cert is really just a regular certificate. Okay, next thing's hybrid key agreement. So SPA 856C defined a couple of approaches for actually doing this. Again, there's been a lot of very, I guess, enlightened, if not positive, support on some of these things from NIST in terms of clarifying. For example, there was a very lengthy argument on a mailing list I won't name about whether or not the PQC value or the non-PQC value should come first when you combine them, and NIST very politely pointed out that it actually didn't matter, which is good. Because what it also means is that if you're trying to do hybrid key agreement now in a certified environment, as long as one of the implementations you're using is certified, you can actually implement a non-certified implementation of MLChem, for example, and we do that with our FIPS API now, because obviously a lot of people are very concerned about the possibility of capture then decrypt. So there's been like this massive adoption of hybrid MLChem. And yeah, the nice thing is that you don't need to worry about the order. So we actually have support for that via a thing called the hybrid value parameter spec, which essentially gives you the facility that's in described in SPA 856C. And again, it's kind of like what you'd expect. The only weird thing, of course, is that you have to do 2 steps at the start where you're actually injecting your shared secret, which is generated using the chem. One interesting thing I'd say about this, I mean, you couldn't necessarily do, well, you could do it with elliptic curve, but it'd be much easier with regular Diffie-Hellman. While I did say before there isn't actually any mechanism for doing multi-party key agreement, if a multi-party group were willing to get together and go, you're the PQC guy, you could actually do a multi-party protocol based on this as well. Anyway, timestamping. So, this is the last one. Of course, we've got a lot of timestamps. We're all going to get really, really upset if these things suddenly become invalid. As it happens, there's been people thinking about this for a while. I mean, RFC 4998, evidence record syntax, actually came out in, I think, around 2010. I mean, you can just tell by the number it's quite old, because, I mean, the RFCs are now well into the 9000s. It also allows you to sign bundles of documents by using a Merkle tree. So, you know, like all great modern cryptographic standards, it comes from the 70s, which is kind of cool, really. It wasn't just about ABBA and platform shoes. Anyway, and then there's a mechanism for provided as well for refreshing an archive timestamp. So you can actually preserve the original timestamp, but give it some additional protection. So yeah, the two situations that basically arise with timestamp renewal are, you might have an issue with the actual hash algorithm, which is to say the hash algorithm you used originally was regarded as weak, and there's also possibilities of an issue with the signature. And evidence record syntax actually provides ways of dealing with all of this. So there's a structure called an archive timestamp chain, which is just basically a sequence of archive timestamps which allow you to use the same hash algorithm but revise the signatures. And then there's another one which is the archive timestamp sequence, which is a sequence of archive timestamp chains. And yeah, each time you rotate your hash algorithm, basically you end up with another one of these. So in its simplest form, an archive timestamp is just simply a timestamp representing a single document. As I said, you know, if you've got multiple documents that you want to group together and you just want to send one timestamp request, you actually end up with this Merkle-like structure. And you generate a single timestamp for the root of your Merkle tree, and then you basically distribute the Merkle tree amongst the timestamp records that are actually inside the archive timestamp. So basically, we've got a couple of ways of building things, either, as I said, groups or actual individual objects. So you can also, if you want to, you know, take a bundle of documents and actually just give them a single hash and make them part of the Merkle tree, or you can have every single document in your list that's part of the Merkle tree. It kind of depends on the dependencies between the documents as to why you would do that or not. The only group that we're aware of that's actually using this in action is in Germany. It's a German government thing. But we are seeing other people picking this up now because this issue of expiring timestamps is starting to become relevant. So we have two classes which actually support both those constructs. There's ERS data, which is just a simple one for specifying that's actually a leaf. And then there's ERS group data, which specifies a group of leaf nodes that have a common parent. So that actually ends up being one single node in your Merkle tree. And then the ERS archive timestamp generator, given our penchant for calling things generators, is then used to bring the data objects and data object groups together to produce the final archive timestamp. So here's a simple example of the setup. That dot is me not knowing how to use PowerPoint. It's not a record indicator or something. But other than that, this is fairly straightforward. As you say, you just create the generator, you specify the digest you're going to use by using a digest calculator. You add your documents. And so in this case, we've got two single documents and one document group. And then you basically use your timestamp request generator to generate a timestamp request, which is actually based on the hash of the Merkle tree that you've resulted. And then you send that off to your timestamp thing, which then sends you back the timestamp, which you then bundle into everything else, and you wind up with this completed archive timestamp when the response arrives. And that's really just a matter of you then add that extra information to ERS generator, and it essentially packages all that up for you and then returns it. So yeah, as it says there, it's equivalent to RFC 4998 archive timestamp. And yeah, we have support for LMS, MLDSA, and SLHDSA now with archive timestamp and timestamp generation in the Bouncy Castle APIs. Okay, so TLS. Well, as I said, yep, everyone's really excited about hybrid. And there's even a bit of excitement now about pure ML-Chem. As I said, unfortunately, if you're in a certified environment, it's kind of, you've got to ask permission. I'd recommend doing that rather than pleading for understanding later, because that's the way they tend to react. But yeah, we have support for the ML-Chem algorithms. The SecP256 and SecP384 are two that you can actually use in FIPS now. In this case, though, of course, you have to have a certified version of elliptic curve Diffie-Hellman, and then you have your actual chem algorithm. X25519, for reasons which I don't fully comprehend, but it might have to do with the fact that the SP56A, 856A is really chunky, and they haven't gotten around to rewriting it. The X, even though Edwards curves are accepted by FIPS for signature purposes now, they're still not accepted for doing key agreement. But yeah, the two at the bottom, as I said, the elliptic curve Diffie-Hellman ones you can actually use today. As you note, these are all in drafts, but yeah, as I said, everyone's very concerned about capture then decrypt, so these are actually quite widely used. I think Cloudflare shows that, there's at least half the traffic that's flying around now or something is actually using them. So interop has been exciting, but a lot less exciting than we thought. There's been a very good team with the IETF, which has met at the hackathons, the PQC hackathon group, which I'm also a member of. And we've been able to work together to basically make sure that the certificates that we're generating are all the same, and we can verify everyone else's certificates and keys. There was one funny thing about this. I know I mentioned before, there's the issue with Chimera with the TBS, pre-TBS certificate structure. So while that's actually in the standard, as it turned out, of the 6 of us that implemented Chimera the first time round, 5 of us, including myself, got it wrong. There's just this last guy. There's always one. And then when we realized by looking in the standard again what had actually happened, yeah, we sorted it out. But I think that's one of the other things about Chimera, in a sense, the fact that this pre-TBS thing has been introduced, it does add a level of complexity, which I think for people that...
One guy who did it wrong, quote, right, as opposed to you all doing it wrong the same way and finding out many years later.
Yeah, that's right. I mean, yeah, we're very lucky. Oh no, there were high fives all round after we worked out what was wrong, because, initially when the thing failed, you go, oh, nah, it's got to be right. Yeah, I did it with Mike. He says it's like this. Yeah. And he goes, oh, no, I think you're fine. And, so you go, standard, read it. And then you go, oh. But that's life. But as you say, I mean, if no one had gotten it correct, there'd be test data going out now, which would be completely wrong. There's some very strange issues with Falcon, because the Falcon standard specifies this different encoding depending on whether you're generating an attached or detached signature. I'm not sure why they did that. I'm sure they thought it was a good idea, and maybe for whatever it was they were doing it for, it was a good idea. But we've had reports, for example, where there's a JavaScript library that generates Falcon signatures. It won't interoperate with Bouncy Castle, but the reason it won't interoperate is because this initial byte is different, because they're generating attached signatures in a detached fashion, whereas we're actually generating detached signatures correctly. Well, anyway, that's our story. But, I think there's some confusion, and we really have to just wait for NIST to release it so that we can actually see what the proper encoding is going to be. There haven't been many issues with TLS. Most of the time when we've tried to interact with someone who's implementing either straight MLChem or hybrid MLChem, it's just worked out of the box. So performance, yeah, look, we've still got progress to make. There's some interesting avenues for improving the performance of these algorithms. For example, FIPS Pub 203, Pub 204 and 205 all state that in some cases, if you can do something that's mathematically equivalent to what's in the standard, that's acceptable. That's been pointed out that in a few cases, the actual shake algorithm is used for generating essentially pseudo-randomness. If you had access to a high-speed random number generator, which was high quality, you could actually get real randomness and replace the pseudo-randomness with that, saving yourself all the shake calculations. We've actually had some goes using ARM, because we've done a bit of work on native support now on the BC APIs. But basically we found that if all you worry about is just trying to accelerate the primitive, the cost of crossing the JVM boundary is so high that if you're lucky, you get equivalent level performance. If you're unlucky, it's actually slower. We have found though that if you actually can wrap MLChem's maths library in total, like the underlying maths, the improvement is between 7 and 9 times what you get with Java. MLDSA, it's around 3 times. It's not such a big thing. So I think for us, in terms of where we're going to go next in the FIPS component, as far as native goes, we'll probably try and produce a native implementation of MLChem, or at least its maths library that we can use. And so here's some additional resources. We have a thing called the PQC Almanac now, which has basically got some handy-dandy descriptions of all the algorithms and then a pile of examples written using the Bouncy Castle APIs. There's examples in there for both Java and C#. And yeah, the source code, of course, is online as well, if you would like to download it.
Hello. So you mentioned ERS
Yep.
as the way to add new timestamps. What is this like? How it compares to CADES? CAI?
I don't. We actually do have some support for CADES, but yeah, I don't have any experience at actually using it directly. As I said, in our case, we ended up adding ERS because there was a German government group that were actually quite excited about it. So I guess probably depending on what you're doing, I think it's like most things, there'll be reasons for using one rather than the other.
Like the point is that like it was designed from the beginning to have support for like assumed that like the algorithms will be broken. So
Yep.
from the very beginning they had those archival timestamps over timestamps.
Does it support the Merkle tree construct?
No, I don't think so.
Yeah, because the Merkle tree thing is kind of neat, I will say that. Yeah. Yep.
Thanks a lot for sharing. Short question. You mentioned the mu way of doing prehashes, but did I miss it? You didn't touch upon the standardized prehash MLDSA from the standard, which does not need the mu strange input.
Yeah, I didn't actually mention it, but yeah, we do support that.
Okay,
So
that's almost.
the pre-hash versions are supported. As I mentioned earlier, like one of the things that pre-hash actually solves for you is if you're in an environment where you don't actually have access to the public key, so you can't do the mu calculation, it will actually allow you to get across the line. But I would say, and certainly with SLH DSA, because of the need to read the message twice, I think pre-hashing is still very much a thing there. But when NIST allowed for the mu calculation to be split across implementations, a lot of the need for pre-hashing in MLDSA actually, I think, disappeared.
Hi, David. A question for another David about a detail. And you mentioned that in PKCS10 with CAM public keys, you can still do the signature, but how do you get around the problem that the CSR in this format usually is just needs to be self-signed?
So that's the thing, really. What you've got is a counter signature if you're using PKCS10 with a CAM key. It's in fact, I think there's always been a way of doing that in general. It's just in the case of an actual CAM, it's mandatory. The only way that you can do effective proof of possession, though, with a CAM is you send back an encrypted certificate and then get the other person to send you back a hash, because or the certificate. Because the issue that you have if you don't have that additional step and you're trying to be a CA is you might wind up publishing something where the other party is just playing games and doesn't actually have a private key that's associated with it. But they're trying to convince somebody else that some other identity has a particular public key for usually nefarious reasons. It's unlikely to be an April Fool's joke when it's something like that.